In the previous videos I've got as far as doing some work on the cases, and in the recent videos I've been looking at the central processing board. As I mentioned, there are multiple processors in an MDS system, and the central processor board, which is this board, is the main control unit within the overall system. It's responsible for issuing commands and governing the way that the system functions. In a recent video I showed hooking up the power supply to the test jig, and I was very careful and went through the schematic very carefully to make sure that all the connections were correct. And just a quick note on that as to why I tend to take so much time and trouble doing that. I currently have a number of these units to work on, and I was provided with some notes along with the boxes of parts and the chassis. Quite a bit of testing has been done on some of the units already, but in the notes it indicates that these units are Intel MDS Model 231s, which is the 240 volt version of the 230, and that is indeed what is written in the corner of the schematic. It's quite a number of years since I worked on these, so if I tell you things aren't correct, I will come back at some point and correct them or make additional comments. But from what I recall, there were two major types of central processor board. There was one that was referred to as the IPB, which was the integrated processor board, and there was one that was referred to as the IPC, which was the integrated processor card. Quite similar, they performed really the same function within the machine. The main difference was the IPB had an 8080 processor and the IPC had an 8085 processor. This is an IPC, and the reason it confuses me a little bit is because the IPCs, from what I recall, were originally only fitted to the 225 and 226 models of the MDS. And checking the rear panels on the chassis I have, it does indeed say 225 and 226, so I was a bit confused as to quite what we're looking at. But as I did say in the first video in this series, there's a lot of grey areas and ambiguity over part numbering and the way that that system worked out over the years with machines being updated and upgraded. So that's why I was so careful to check the schematic, and I advise you do that with any old equipment. It's been around the houses quite a number of times, and exactly what you're looking at may not be quite what you're expecting, so it's as well to look into it in depth before applying power or making any modifications to it. So in the last video I applied power to this board and it appeared to be working. We were getting some activity, but of course the issue now is how to go about testing this, and the methods I use aren't as ever necessarily the best, or what I'm suggesting you do. This is just one method that can be used. The method you use is up to you, it depends on the equipment you have and how you want to go about this. But what I normally do with a system like this is I will start by getting it fundamentally working, which we have. I then pull out the ROM and I extract the code from the ROM and pass it through a disassembler. And in a recent video I demonstrated how I go about using the logic analyzer and the disassembled code to go through fault finding on a particular machine. And this is a very good example of where that's quite a good method for fault finding and testing. So that's what I'm going to be introducing in this video, how I'm going about doing that, and we'll look at the logic analyzer and see if we can capture the boot up part of the code. So as I've said previously, the architecture on these machines is a bit odd, and in the ROM there are two distinct sections of code. There is one for the boot part of the code, so boot and monitor, and there's another one that is for diagnostics, and they're completely separate sections of code, but they're in the same ROM. So what I'll be doing in this video is extracting the code from this ROM. We'll have a look and see if we can find a way to determine where this is mapped to on the board, and then we'll hook up the analyzer and see if we can follow the boot up code and see if it matches what we're expecting. Now I do of course have the schematic for this board, so I could just look at that, and we will be cross-referencing that to make sure I've got this right, but I just wanted to consolidate the information I'd given about using a logic analyzer to do this sort of work, just in case you don't have the schematic or if you don't have a listing for the firmware. So step one is to read the code from the ROM. I've been requested to show the process of converting that into a listing. I won't do that in this video, but I will do a separate video for that. It's very straightforward to do. I've also been asked which disassembler I use, and I use a number of different ones. In the video where I demonstrated this recently, I used a disassembler that I downloaded, and I also wrote a small disassembler to do some specific disassembling of part of the code, and I'll explain why in this video I sometimes do that. So step one, as I say, is to get the code. So I've done that. I've passed it through a disassembler. You can see here which one it is. Hopefully no one's going to have any issues with copyright on this. If you own the copyright on this and you want me to remove this or add any comments, then please let me know. But what we end up with is something that looks like this. We pass this through the disassembler, and as usual we get the disassembled code. Unfortunately, you do need to be fairly careful when you're doing this. So firstly, where is the origin for the code? So initially I've set the origin here, as you can see it's E000, but it doesn't seem to match what we're seeing within the code. So if we look at the first instruction, it's a jump to E806, but if we go through to address E806 in the code, then what we end up with is something that doesn't really seem to make a great deal of sense for bootup. So we have this here, and we can see that it's a series of jump instructions. That this can be a kind of lookup table for jump destinations, but this doesn't seem to be right for bootup. What you normally expect to see in a system like this, almost straight away, usually the first instruction is to disable the interrupt so that you don't get any ambiguity while you're trying to initialize the system. And that's not what is visible here. Now, one of the problems that disassemblers have is that you get a processor like the 8085, and some instructions are 1 byte, and some instructions are 2 bytes, and some instructions are 3 bytes. And the disassembler doesn't ahead of time know if, when it starts reading an instruction, whether it's a single byte instruction, a 2 byte instruction, or a 3 byte instruction. So it kind of does it in sometimes multiple passes, and it tries to figure out, based on almost the context of the code, what a particular instruction is supposed to be. And it doesn't always get it right. And in this case, it hasn't got it right. I can see that just by reading through this, and I'll explain why as we go through this. Also, trying to figure out the address that this is mapped to is not quite as obvious on this particular machine. This particular disassembler is very good. It also generates a symbol table. A symbol table is just a list of all the addresses that have specific potential meanings, such as destinations for jumps, data values, that sort of thing. And if we look through here, we can ignore all these first ones. They're not really meaningful in the context of what we're looking at. But if we notice that the first that seem to be actual code addresses is at E806. Now that tends to indicate that possibly the origin for this code is at E800. And if we go through, then we can see that at the end of the table we end up getting into the Fs. So it's unlikely in this ROM that the entire code is within a single 1000 byte boundary, 1000 hex that is. So we need to find where this is mapped to. As I say, I've got the schematics, so I could just refer to those, but just for a bit of fun, or if you don't have the schematics, we'll use the analyzer to figure out where the address mapping is for this machine. So the first thing I need to do is refit the ROM. I'll then fit a test clip to the ROM, and we'll hook up the analyzer and see if we can capture the start address for this particular ROM and then figure out where it's mapped to. Okay, so I've got the test clip on the ROM. The next thing we have to do is figure out how we're going to trigger on this ROM so we know when it's been addressed. Okay, so if we look at the data sheet for this device, it's a 2732 and pin 18 is the enable pin. So we'll use that pin to trigger the analyzer, and we can then look at the address bus to see what address the ROM is mapped to as far as the processor is concerned. So we'll use the next available pin on pod 2. We'll connect that to pin 18. Okay, and so what we'll do now is look at the analyzer, and what we have hooked up now are the address data lines and the chip select line for the ROM, and that's all we need, in theory at least, to check the mapping for the ROM. Okay, I've got the analyzer switched on. I've reloaded the project that we created in the previous video. If we go through to format, we want to assign a new label. So in this case, we'll just use the next one down, and we'll call it not chip select. And this will be, just need to select the correct pod. That's pod 2 we're looking at, and it's input number 1. So that's all we need to do as far as configuring the analyzer in terms of defining the input. The next thing we want to do is go to trigger, and so what we want to do now is to modify the trigger to capture the point we're interested in. So firstly, I'll get rid of the reset and set that to don't care. We are interested in the chip select going active low. Now unfortunately we can't leave it like that. If we just try resetting the machine like this, then the chip select is low when it powers up, so we just capture a lot of nothing at the beginning of the boot up sequence. But what we do know is we're interested in capturing a particular address, and looking at the listing, it's looking like the address that we're interested in is going to be E800, and I'm assuming that the jump to E806 is just jumping through to address 6. This is why I think this is wrong. I don't think this is the right interpretation of this particular part of code. It doesn't seem to make any sense, but what we'll do is we'll capture the data and see what instruction we're getting at address E800 and see if we do indeed hit that address. So I'll set the address to E800, and now we'll try and trigger the machine. So I'll now boot up the processor and see if we capture anything, and indeed we have, and it's actually the right address, so that's looking quite promising. Okay, so what we'll do now is, we believe the first instruction is a jump to E806, so we'll now set that as the destination for the trigger. Rearm the analyzer, and I'll reset the board. The trigger point. So what we could start doing from this point is working our way through the code, seeing how it relates to the decompiled listing that we have. But as I said, I believe that it's incorrect. If we look back at the decompiled listing, then we can see that it doesn't match what we're seeing in the listing, and more importantly, this initial construct doesn't make any sense. So what we can start doing from this point is working our way through the code, as I showed in the video where I demonstrated using this technique. And really what you do is just work your way through the code using the analyzer to step through. It's almost like an ICE system. The only difference, of course, is we don't have any control from the analyzer to the target board, but we can see what's actually happened and trace through the code and see if it matches. Now, it doesn't match what we're seeing here. It's completely different, and as I said earlier, this doesn't make a lot of sense. This construct doesn't really make much sense. We now know the address that we're mapped to, and the start of the ROM is indeed at E800. So we now know at least where the ROM is and what the addresses mean within the ROM. But the values we're seeing on the analyzer don't match what we're seeing here. And what we're seeing on the analyzer makes perfect sense. We believe that we're jumping initially to E806, and the first instruction that we're loading from there is F3. So this is a bit confusing. As I said, the process is a bit odd, and the data value under the address is of course part of the address, so we have to ignore that, and you have to look at the next part, and then you have to ignore the address, because that's a combination of the actual address and the data, because the data and the lower 8 bits of the address are shared. So you have to kind of go diagonally across and leapfrog your way across the code on this particular processor. So in other words, what we're seeing here is that at address E806 we are obtaining a data value from ROM of F3, and if you're not familiar with the 8085, F3 is a disable interrupts instruction, and that is exactly what we would expect to see as the first instruction in pretty much any 8085 system where you want to make sure that the initialization proceeds as it should. You can then work your way through doing the same thing. We got to address E807, and again you need to ignore the 07, and the next value we're reading is 3E. As I say, it's a bit non-intuitive with this particular processor, but that's the way it works, and it is quite easy once you get used to it to walk your way through the code. Luckily, with the MDS system, the full listing for this ROM is available online, so of course I have a copy of it. It is quite a big document. One of the first things to say is there is more than one version of this, so we need to figure out which particular version we need to be looking at. This is another reason for using this particular technique and doing the initial investigation by disassembling the code. So we end up with a fairly simple disassembly, but if we look through this and we get to the relevant page, then what we will find is this. And when we look down through it, so this is the disassembly for the particular ROM that I have in this machine, and if we scroll all the way down, we'll see down here it says version or v1.3. So it's saying here series 2 monitor version 1.3, so we know that this is version 1.3 firmware. So that's the version that I have here. As I say, it's quite a big document, but it's version 1.3, so I know that this is the correct code for the ROM that's in this machine. The next thing to do is see if what we're seeing on the screen actually makes sense. Does it match what we're expecting to see when we start running through the code? So I've printed off the first section of actual code. There's a lot of header information, initialization values, that sort of thing. But ultimately we end up jumping down to here. This is address E806, which is the address we see on the analyzer, and you can see that the first instruction that we load should be F3, and that is indeed the value that we're seeing, which is F3. And further, if we look across, we know it's a DI instruction, which is disable interrupts. So that makes perfect sense. If we go across to the next address, which is E807, then we can see in the listing E807 the data value should be 3E, and it is indeed 3E. And if we go across to E808, it should be followed by 02. So we've got 02, and that is indeed what we're seeing in the listing. And luckily I didn't do this, this was one I downloaded, but it's very detailed. It's pretty much the original source code. This is one of the good things with machines like the MDS. There's an awful lot of work being done by a lot of very smart people to help maintain these machines. So it's always worth looking for this. We still needed to go through the disassembly of what we have here to make sure we have the correct version. There's nothing printed on the ROM. Now of course, if the MDS system was running, then in theory it would tell us on the screen of the MDS what the version of the monitor is, but we haven't got that far yet. We're going through it from the ground up, so to speak, and so this is a very useful technique to use in finding out exactly what's going on. Now of course, because we've got to this point, it means we can work our way through the code, find out exactly what's going on, look for the relevant sections in the code of things we want to test. If we needed to, and especially if we didn't have this, we could write our own ROM test routines, as I did for the HP calculator I repaired recently, or we could connect the Fluke 9010A and run some test code from there, in a similar way that I tested the REN memory recently. So there's many tools we have at our disposal. The central one to all of this is the logic analyzer, so that we can see exactly what's going on. We can find out where devices are mapped to, we can see if they're working, we can see if the values they're getting back are meaningful. And with a system like the MDS, the logic analyzer will become invaluable, as you see as we work our way through it. Because of the multi-bus nature of the MDS, then you have to try to figure out if the commands and data that are flowing across the bus between the individual processing modules are correct. And if they're not correct, you have to try and figure out which module is at fault. And it's not always as straightforward as it might first sound. Okay, that's it for this video. As ever, if you want more information or more detail on any aspects of this, then let me know. But the next step, I'll be working my way through this code. I won't do that on camera, it'll get fairly tedious and it's quite a lengthy process. But once I'm happy that this card is working, I can start reassembling one of the MDS units and we can start looking at the in-out board